accepted. And there will be a chance to ask questions at the end. Martin Fertl obtained his PhD by the ETH in Zurich in 2014 with a thesis on a laser-based mercury connectometer for the neutron-electron dipole moment search at the Pulsar Institute in Switzerland. He then moved to the University of Washington in Seattle as postdoc until 2016. That was the time when I was also a postdoc there. Until 2019, he kept working at the University of Washington, but as assistant professor. During his time at the University of Washington, he worked at the g-2 experiment, which is the topic of this seminar, and has the goal of measuring the anomalous magnetic dipole moment of the muon. And he also worked at the Project 8 experiment, aiming to measure the absolute neutrino mass using tritium beta decays and cyclotron radiation emission spectroscopy. Since 2019, he is a professor at the Johannes Gutenberg University in Mainz, where he keeps working on the g-2 and Project 8 experiment, and also at Tau SPECT that deals with the determination of the free neutron lifetime. So just add that it's a pleasure for us to have you here, Martin, and I let you start.
Thank you, Clara, for the very nice introduction and for the invitation and giving me actually the chance to talk about our very first results of the Muon g-2 experiment at Fermilab. So let me give you an outline of the presentation. I will quickly review the status of the theory and the experiment before last week. I want to introduce you to the Muon g-2 experiment at Fermilab, how it's built, and then go into the data analysis chain. Is the feedback from me, or is some of the mics open? Clara, can you verify that?
I can mute someone.
Okay,
yeah.
Thank you. And then I will talk about the data analysis chain, basically, that we had to develop to extract the two ingredients that we in our experiment measure. So I will be quick here. I mean, we all know the standard model of particle physics, and we really love it because it's our best model we have right now, but we know it's incomplete. And precision frontier experiments like the Muon g-2 experiment, they actually try to provide the most stringent tests of the most accurate predictions of the standard model. And one, not if the most accurate prediction of the standard model actually concerns the magnetic moments of charged leptons. So for a charged particle with a magnetic dipole moment and spin, we all know this, we can have write down a relation that scales or that tells us how strong the magnetic dipole moment is in relation to the spin, and it scales with the Landé G factor. So for a point like charged lepton with spin 1/2, Dirac already in 1928 predicted that this G factor should actually be 2. And in his famous paper of 1928, he points out also, not in addition that like the G factor should be 2, but that there's another moment of the electron that he wasn't able to deal with or handle it, which is like an electric dipole moment. And that's another one of these searches that Clara just mentioned that I've been working on, because these also provide a standard, very powerful test of the standard model. So let's jump ahead by roughly 20 years in history and look at the contributions to the anomalous magnetic moment. They can be very precisely calculated, and that's why it's so attractive to actually also perform a measurement of this quantity. So in a modern Feynman diagram picture, Dirac's G = 2 is actually describing just the interaction of the muon with the virtual photon of the magnetic field and then emitting it on the tree level. Today, we have learned over the last couple of decades that actually there's contributions, so-called radiative contributions to the anomalous magnetic moment, and all the known and also unknown interactions contribute to the value of A mu. And so I just highlight here contributions from quantum electrodynamics, contributions, some selected of the weak interaction. And then we also have contributions from hadronic physics, as you can see on the rightmost diagram. The dominant factor or the dominant contribution to A mu we know since 1947, when Schwinger basically calculated the first order QED correction alpha over 2 pi. And it's chiseled into his tombstone because of the importance. Since then, a lot more calculations have been performed over the decades, and the most recent evaluation of the standard model prediction was actually performed by the so-called Muon g-2 theory initiative, which set out to update the prediction for the upcoming Fermilab experiment. So in units of 10 to the minus 11, the QED contribution has been calculated up to alpha over 5, which is more than 12,000 diagrams. And you can see why it's the lion's share of the effect. The uncertainty is completely negligible, as you will see in a moment. Then we have contributions from the electroweak interaction. And the most troublesome with the largest uncertainties are actually the contributions from hadronic physics. So the lowest order hadronic vacuum polarization, for example, is shown in a diagram on the right-hand side, when in this blob, there is not leptons running around, but strongly interacting particles, quark pairs. Then there's also contribution so-called that's called hadronic light by light scattering, where you actually have 3 photons coupled to this hadronic loop, which then subsequently couples to the virtual photon of the magnetic field. You can already see that the largest uncertainty contributions come from these 2 contributions. It's hadronic physics. And so the latest standard model prediction is shown here. It's this 11, 65, 91, 810, with an uncertainty of roughly 370 parts per billion. So we can compare the standard model prediction with the experiment. And in this comparison, up to last week, there was basically only the latest Brookhaven experiment, BNL E821 value. And you can see how over the last 2 decades, basically, the theory of prediction has moved and has shrunken its error bar. And the latest comparison between the Brookhaven experiment and the standard model prediction left us with this discrepancy of roughly 280 units of 10 to the minus 11, which corresponds to 3.7 sigma deviation between the standard model prediction and the Brookhaven experiment. And so at Fermilab, we actually have the goal to reduce the experimental uncertainty by a factor of 4, 240 parts per billion. If you want a short run-up of our experiment and explanation, I recommend you look at this g-2 PhD comic that was co-published with our release last week. But let's go a little bit deeper into the details here. So actually what we do is we basically compare 2 clocks of a charged lepton. If we take a relativistic lepton and have it circulating in a homogeneous magnetic field, it will experience 2 well-known effects. It will undergo cyclotron motion with the well-known cyclotron frequency, which is just a combination of its charge, its mass, and its relativistic gamma factor, and proportional to the magnetic field. The second effect is also spin precession, which is due to the coupling of the magnetic moment to the magnetic field. And this is also well characterized. We get the Larmor precession and the Thomas precession. So you get a spin precession term on the right-hand side. Amazingly, if you take the difference between these 2 frequencies, then you get another frequency that is directly proportional to the deviation of g from the prediction of 2. So to the quantum corrections, g-2 over 2, which we call little a, the anomalous magnetic moment. And one of the magics of our experiments that is actually working so well is that this frequency difference is independent of the particle momentum. And if we take a picture, what does it mean? If g is larger than 2, this means that the spin is actually precessing a little bit faster than the momentum vector of the muon around the storage ring. And this is exactly what we want to measure. We have to confine our muons actually in a superposition of electric and magnetic fields. And this introduces a couple of correction terms to this very simple frequency expression. But what we can do is we can actually, first of all, identify the non-relativistic limit and the ideal circular motion limit. And then we get corrections that we call the pitch correction, which is due to the vertical motion of the muons along the magnetic field lines. And the third term in this expression is a correction that results from relativistically generated magnetic fields due to the electric fields that we use to focus our muons and confine the muons in the storage ring. So what we actually need in our experiment is a pristine measurement of the magnetic field map in the magnet, and its temporal evolution, we need to understand the complex beam dynamics of the muons as they circulate in our storage ring. And to assess the last effect or to minimize it, our experiment is actually running at the so-called magic momentum. So we choose the momentum of the muon such that the gamma factor is roughly 29.3, which to first order exactly cancels the extra contribution of the anomalous magnetic moment. So let me show you a picture of the muon G-2 experiment at Fermilab, as it's roughly currently looking. So this is the storage ring that we employ to do our measurements. But this is not like assembled by one person, but we have a whole collaboration, the so-called Muon G-2 collaboration. And it's about 200 collaborators from 35 institutions around the world, originating from 7 countries, that we assembled with many different backgrounds of expertise to actually be able to perform the experiment. So let's start with the accelerator physics expertise at Fermilab. That's where the experiment is located. And the new Fermilab Muon campus basically provides us with the bright source of the pulse-polarized muons that we need for our experiments. So we start out by striking 8 GeV protons on a target, and with a bunch length of roughly 120 nanoseconds. These bunches, we take 8 of them, are separated by 10 milliseconds, and we take a second bunch trained 200 milliseconds later to avoid pileup in our experiment and just to optimize the experiment performance. So we produce pions in the target, and these positive pions, they decay in a momentum selective beamline in which all or a lot of the debris from the target was actually focused in. And when the positive pions decay due to the weak interaction, they actually produce left-handed polarized muons, positive muons, with nearly 100% polarization. And the neutrino just flies away. So what we actually have in the muon system, because of the weak interaction, we have a self-analyzing spin polarimeter, which is really, really nice. So the particles that are created in the target are focused in this beamline and then transported at the magic momentum roughly of 3.9094 GeV with a spread of 2%. But at the end of this beamline combination, there's only about 80% of the pions have decayed away and produced muons. And the rest is roughly 20% of beam contamination, which was a problem at the Brookhaven experiment. And this contamination are already decay positrons from the muons. There's still surviving pions in the beam, and there's protons from the primary beam. And so to purify the beam, what we actually do is we send it around an energy dispersive delivery ring. In this one, the muons, they are slightly faster than the protons because they are less heavy. They can outrun the protons, and we can kick the protons out of the beam. And the rest of the pions can actually decay away, so we get a pure lepton beam, which is roughly 60 to 70% muons. So what do we do with this lepton beam? We inject it into our storage ring. But the storage ring actually had to be transported from Brookhaven National Lab all the way around the east coast of the US up the Mississippi to Fermilab. And you can see one of the pictures here on the right-hand side, which shows part of the superconducting coil system on a barge. It arrived at Fermilab in 2013, and then over the course of 14, it was reassembled, and I show you basically a picture of the storage ring, how it looked like in 2017. So our particles come from the delivery ring. From the tunnel, you can see the last focusing elements of the beamline, and they have already the right momentum to be stored. And we store the particles in this superconducting magnet that consists of 3 cryostats with 4 superconducting coils, each running at more than 5,000 amps. And it produces a 1.45 Tesla nominally vertical magnetic field. And the area, or the diameter of the storage area for the muons is this red dot here, which is 90 millimeters. And there's roughly 180 millimeter gap for the rest of the vacuum chambers in the opening of the C-shaped magnet. To make actually the muons travel to the inside of the storage ring, we have to provide them a magnetic field-free region that they can actually travel through the backleg of the magnet in a straight fashion. And we do this with the superconducting inflector magnet that cancels locally the magnetic field in the iron and provides in this beam channel a field-free region so that the muons can actually travel to the inside and are not deflected into the iron of the magnet. The next thing we need is a very fast kicker, because we have to put the muons on their nominal storage orbit with about within a 1 revolution, which is the cyclotron period is roughly 150 nanoseconds. And why do we have to do that? If we inject the beam and we are just in a homogeneous magnetic field, after one turn, you can see on the red orbit, we would just hit the backside of the inflector again. And so to avoid this, we actually have to displace the muon beam from the injection orbit to the storage orbit. And we do this with the kicker. And you can see the kicker plates here that run a current through these plates that locally decreases the magnetic field and deflects the beam outwards. And this all in roughly 150 nanoseconds. You can see the pulse train on the right-hand side. The red one is actually the muon distribution, and the black one is the kicker signal on the plates, the current. So ideally, it would just rise within one cyclotron period, but this is really, really challenging, and so there's some ringing at the end. But this causes the beam to be displaced on its nominal radial storage orbit. To avoid the muons basically spiraling out of the magnet vertically, what we do is we have so-called electrostatic quadrupoles. On the right-hand side, you can see the quadrupole plates, and the top and the bottom one we actually charge with a positive high voltage. These plates cover roughly 43% of the ring, and our positive muons are basically reflected from the top and bottom plate or repelled, and so we get a vertical focusing and a confinement of the muon beam in the circle around the ring. They undergo decay, and the decay positrons that they emit, we detect in actually 24 calorimeter stations that are positioned on the inside of the ring. And each of these calorimeters consists of a 9x6 array of lead fluoride crystals, which you can see a close-up on the left-hand side. And these are pure Cherenkov detectors, so they are very, very fast. The decay positrons, they actually carry information about the relative orientation of the positron's momentum vector and the original muon spin, because again of weak interaction. You can see this on the left in this scheme here, that high energy positrons are preferentially emitted, sorry for the coffee machine here, along the spin direction of the positive muons. If you look at the acceptance and take this into account of each calorimeter, you can see that there is sorry, wrong direction, that you have a modulation in the count rate of high energy positrons. So the spin precession in the muon rest frame is actually transformed to an above energy threshold count rate modulation in the laboratory frame. And it seems that this is a little bit wonky here, this video. Okay, and I have indicated that there's like a 1.7 GeV energy threshold. And to make sure the threshold is always the same and stable, we actually deploy a dedicated laser calibration system for each and every crystal in the calorimeters to make sure that the energy calibration is stable over various timescales from the fill of the magnet over days to hours and months of operation. To actually learn more about the dynamics of the muon beam, we employ the so-called straw tracker stations. And you can see here a cut of a model. In front of 2 of our calorimeter station, we have 8 modules of straw trackers. And with these ones, we can actually reconstruct the flight paths of the decay positrons. And with this information, we can then feed extensive beam dynamic simulations to understand how the beam actually moves around the whole storage ring. And you can see here an inside view, a muon's view of the tracker stations on the right-hand side, and a reconstruction of the beam position over the first 100 microseconds after the injection. And what you can see is that our beam is actually not just static on a circular orbit. No, it actually moves around. It swims left, right, and also up and down. And you can see on the right-hand side, as a function of time, the radial position is actually changing slightly, or like oscillating with these coherent betatron oscillations. And also the RMS of the radial position is changing over time. And so this is our diagnostics tool to learn more about the muon dynamics and the distribution in the storage ring. So now I have introduced you to the basic ingredients of our experiments, and I will go over and talk more about the analysis. But I will not be able to cover all the details of the analysis because, like, we have co-published with the PRL 3 other papers that discuss the magnetic field measurements, the extraction of the anomalous spin precession frequency, and the beam dynamics in a first for physical review. Normally you can just co-publish 1 technical paper. We co-published all 3 of them. And it's more than 100 pages in total, so I cannot cover this by any means here today. So what I will talk about and present you the analysis is only data from run 1 that was taken in 2018. And you can see that by now, this is a plot of like last week, we have collected more than 10 times the statistics of the former Brookhaven experiment. This run 1 is also not a homogeneous data set, but we actually were running in four sub-data sets with different high voltage settings. For example, on the kicker, you can see that we changed the voltages here, and also the voltages that are applied to the plates of the electrostatic quadrupole. And so we have actually 4 different data sets that you have to analyze independently. So the basic idea of our experiment, if we come back to it, is we want to extract the anomalous magnetic moment from a measurement of the anomalous precession frequency and the magnetic field. And to do so, we actually anchor this equation to other high precision measurements and calculations. So we express the electric charge in terms of the magnetic moment of the electron and its g-factor, and the magnetic field we represent as a measurement of a proton precession frequency and the proton magnetic moment in a particular sample. And if we introduce that, we can actually expand this, and we get 4 additional external ingredients to the result that we are interested in. The first one is the ratio of the proton in a shielded sample of water to the electron magnetic moment in hydrogen, which was measured to 10 parts per billion a long time ago. We need a bound state QD calculation, which is basically exact, that relates the magnetic moment of a free electron to the magnetic moment in a hydrogen atom. We take the mass ratio of the muons to the mass of the electron from the muonium hyperfine splitting measurements, and we take the measurement of the g-factor of the electron. And these 4 external inputs to our result, they have a total uncertainty of roughly 24 parts per billion. So our challenge in the experiment is really to extract the ratio of omega A over omega prime tilde. And so this ratio, you can see, it looks like just 2 numbers, but in reality, it's this more complex master formula that we have to tackle and understand, basically, to be able to perform the comparison. So the tools we have to attack each of the individual contributions here is the following. We extract the anomalous spin precession frequency from this wiggle plot that I show you on the left-hand side, and that you most probably have seen already. The correction terms here, due to the muon beam dynamics, we extract from the tracker information, and I will discuss them individually. We also need to know the spatial muon distribution around the ring to know in the end where the muons actually lived and what magnetic field the muons saw on average. For this, we also need to determine the spatial distribution of the magnetic field across the 9 centimeter diameter storage orbit. And we actually have to correct for transient magnetic fields that are only present when the muon beam is stored in the storage ring, but are not present when we measure, for example, this magnetic field distribution map. And then we need to calibrate the magnetic field in absolute terms relative to the other measurements that we are taking as a reference. And the last point is we need to blind our clock, because we really want to be sure that we are not pulled in a certain direction in the analysis. And I will go through these individual parts here of our analysis. But before doing so, I just want to flash you with the uncertainty table from our experiment, from the publication. I want you to take away that basically the experiment currently is completely dominated, the uncertainty, by just the statistics of omega A. You see this is more than 430 parts per billion. The systematics in this case already surpassed the anticipated goal, but on the field side, there is more systematics that we have to work on, and also on the beam dynamics. But takeaway is really that we are working on improving our systematics for run 2 and 5, 2 to 5, and currently we are totally dominated by the statistics. So to extract the anomalous precession frequency, what we do is we build time histogram or histograms of the arrival times of our decay positrons. And you can see one of these for a subrun here on the left-hand side. From the calorimeter information, we actually have 3 different ways to reconstruct the events and put these decay positrons in the histograms here. And then there are 6 independent groups that perform 11 different and independent analyses to extract the omega A frequency. What looks easy here with a naive like 5-parameter fit actually turns out that this wiggle plot encodes a lot of the complex beam dynamics that's really ongoing. And you can see this in the residuals of the fit. If you just ignore the coherent betatron oscillation and, for example, losses of muons, you end up with the red residuals, and you can see clearly these additional frequency components. And so the full fit function actually takes all these beam dynamics aspects into account, that the beam is actually swimming around up and down, and that its widths change. And only if you do that, which is more than 24 parameters typically, then you end up with a flat distribution of residuals that are structureless. And because of the different settings of the kicker and the electrostatic quadrupoles, we had to actually perform 4 separate analyses for run 1A and 1D. And only after extensive systematics checks have been passed, we actually removed what we call a software blinding that was given to the 6 independent groups, while a hardware blinding, which about I will talk later, was still in place. And then we compared the results of these individual analyses, and you can see that most of them are in very good agreement. 10 of them, the last one is a very special type of reconstruction. And then we decided for our publication that we take the results of the statistically most sensitive method, the so-called asymmetry weighted method, which are like indicated here, from 4 different groups. And from this, we derive our statistical uncertainty of roughly 430 parts per billion and roughly 56 parts per billion systematic uncertainty. Already for the predecessor experiments, there have been long known corrections that we have to apply. I mentioned it before, the corrections for the electric field and the pitch. The pitch correction we actually extract from the tracker by measuring the amplitude of the modulation of the swimming in the beam, and we can then derive a correction to the measured frequency, which is as large as 180 parts per billion, but with a small uncertainty of only 13 parts per billion. And then we also have a correction for the electric field. And as you can see here, it's indicated the distribution of the muons in between the quadrupole plates. In our run 1, the beam was actually not yet centered. Our kickers were not strong enough to put the beam in the center. And so there's actually a fairly large correction of roughly 490 parts per billion with an uncertainty of roughly 50 parts per billion. to perform this analysis, we actually need to know what the momentum and distribution and the equilibrium position is. And we do this with an analysis technique that has been long known as the fast rotation analysis. The next correction I want to talk about is actually the phase acceptance correction. So if we go back to look at this Fertl plot, then we can just, for the sake of the argument, take this simple fit function of an exponential decay that is modulated with an amplitude at a frequency omega a and a certain phase. The phase is initially arbitrary, it's just a fit parameter. But if this phase is not stable over time, then if you just perform a Taylor expansion in the cosine, then you can see that actually there is a contribution. The first derivative of the phase in time looks like a shift in the frequency. And so this is really dangerous. If this phase is not stable over the course of your measurement, then that could introduce a systematic bias. And this is one of these effects that we call the early to late effects. The initial phase of the muon ensemble actually, and the one that you detect in your calorimeters, that decay on the decay position of the positrons, of the muons, and then also the decay positron energy. And we have extensive simulation of these properties in the whole experiment. And as I mentioned before, it's not a problem if the muon distribution is stable in time. But actually in run 1, we had a challenge or an issue that on 2 of the 32 electrostatic quadrupole plates, the high voltage resistors failed. And so on the left-hand side, you can see in black the nominal step or nominal shape of the stepping of the voltage, and also the red dashed line. But on the damaged one, which are shown in dash blue and orange, you can see that actually the charging of the plates took much longer. And so this means that we had actually a time-dependent electric field on 2 of these electrostatic quadrupole plates, which caused a vertical displacement of the beam and a change of the beam width. And if you combine this change of the vertical position and the beam width, which were well measured with the tracker, with the simulation that I show on the left-hand side, you actually get a residual effect, which is large. You have to correct the measured frequency by roughly 160 parts per billion with a fairly large uncertainty of 75 parts per billion. So this effect is exclusively for run 1, because then we fix the hardware for run 2 and beyond, and this effect is absent. To really understand this effect, this is one of the parts that took us more than a year to get to the nitty-gritty details of it. And we are happy that we don't have to repeat this for the next analysis phases. Another one of these early to late effects are lost muons, and we have to correct for them. The muons initially, they have a certain phase, but if this phase, as I just mentioned, has a time dependence, this would be a bias. And in a second order effect, there could be such a bias if the phase, the phi naught, is actually dependent on the average momentum of the muon ensemble, and if this average momentum changes over time. And this effect exists. There is a spin momentum correlation from the dipole magnets in the beamline. Basically the same way as the stored muon beam undergoes the anomalous spin precession in the storage ring, in the energy dispersive delivery ring, there's also dipoles. And each time you pass a dipole, you have a little bit of extra spin rotation. And depending on where the muons are born in the beamline, they might pass more or less of these dipole magnets. And so they end up with having a slightly different phase initially. And if then the muons with different momentum components are lost at different rates, then you can get a combined effect. And this was measured and simulated in our experiment. You can see on the right-hand side that high momentum muons are actually lost a little bit faster than low momentum muons. And then you can combine this and obtain a time-dependent phase shift. And you can see here, typically we start at 30 microseconds fitting, that up to like on the order of 200 microseconds, there's a continuous shift. And also this is related to the the instability of the beam dynamics. But in the end, we were able to characterize this very well. And so we have to apply only a small correction of roughly 11 parts per billion with an uncertainty of 5 parts per billion. So let me now change from the denominator of the expression to the denominator and talk a little bit more about the magnetic field and its calibration. So we have a complete chain to calibrate the magnetic field over the spatial and the temporal distribution. So we employ the so-called trolley, which is a semi-automatic device that we can actually pull through the magnet roughly every 3 days when there is no muons stored in the ring. And that allows us to measure the spatial distribution of the magnetic field around the ring with 17 pulsed nuclear magnetic resonance probes. To actually track the magnetic field when there are muons stored in the ring, we use the so-called fixed probe array, which is roughly 400 pulsed nuclear magnetic resonance probes that measure the magnetic field 24/7 around the muon beam, and they sit on the outside of or in the walls of the vacuum chambers surrounding the muon beam. And then we have several calibration setups that actually allows us to transfer the absolute calibration with a so-called plunging probe to the individual 17 probes on the trolley. And we have compared this plunging probe that is deployed in the ring in a very homogeneous section of the field, also to other field standards, for example, like a helium-3 nuclear magnetic resonance magnetometer. But how do we actually obtain the precision magnetic field? And I would just want to give you some information about that. After we assembled the magnet in the very first place, what we did is we put 25 of these NMR probes on this cart that you can see on the left-hand side, and we pulled it around the ring. And so we measured basically what the inhomogeneity level of the magnetic field is. And you can see the free induction decays that you get from the probe on the right-hand side. If these signals are long, the field is homogeneous. If they have many zero crossings, the local field across the probe is very inhomogeneous. And so this gives you basically the recipe then for adjusting several knobs in the ring, which are mainly ferromagnetic parts and iron, to adjust the pole piece orientation, their tilt angles, and also wedge pieces to make as homogeneous magnetic field across the gap of the magnet. One technique that we developed for the Fermilab experiment, and is novel, is that we basically provided more than 10,000 iron foil strips that we cut on a laser cutter and weighed very carefully to shim out the residual magnetic field inhomogeneities. So you can see here in the center that we glued these iron foil strips on G10 boards that we then glued on the surface of the pole pieces of the magnet. Let me just give you an impression here of what we did in this video. So in red is our magnetic field, in blue the Brookhaven achieved one. And as we glued the iron strips on the pole faces, we were really able to nail down the magnetic field and homogenize it by a factor of roughly 3 better. The trolley that I mentioned runs around or is pulled around the magnet every 3 days. And the information we get from these 70 probes, we then decompose in so-called 2D spatial multipoles. So we have a description of the magnetic field in terms of a dipole component, of a normal quadrupole component, which is a change of the magnetic field strength from the left to the right. And skew quadrupole components are shown here. There's higher order components that we take into account. And so from over 9,000 azimuthal measurement positions, we can actually then derive a typical, I show here, average field map around the ring. And you can see the color map modulates from roughly -1.2 to 1.2 ppm. And that's the field homogeneity we achieve around the ring. We use this, as I mentioned before, the fixed probe array to track the magnetic field in time. And I just want to give you one example here, how we track, sorry, here we go. The different magnetic multipole components in time. And I give you as an example only the first or the most important components, the dipole and the normal quadrupole, over the course of the 4 data sets of run 1. You can see the whole data set spread in total over 70 days, but there is a large gap break in between. And you can see that in particular in the normal quadrupole that there's also diurnal modulation in the data that was just there because the temperature of the magnet was not yet as stable as we anticipated it to be. Now let's go to the next step and talk about the averaging of the magnetic field actually with the muon distribution, which also is very important for the denominator here. I mentioned before that we use the so-called straw trackers to determine the distribution of the muon beam in the storage region, and I just repeat this picture. And then we can actually calculate with the input of the beam dynamic simulation the average position of the beam and fold this with the magnetic field map that we have extracted. And the result you can see on the right-hand side. Overlaid, you see the field homogeneity map that we use for the analysis. And again, you see that the beam is actually off center towards the outside of the ring. This whole procedure contributes roughly 56 parts per billion uncertainty, which includes the calibration of the magnetic field probes, the field maps, but also the alignment of the tracker and the beam dynamics model. The precision magnetic field was affected by 2 systematic effects that are transients and that I just want to discuss here quickly. So one is due to the electrostatic kicker quadrupoles, and to clarify the term, these quadrupoles are only static on the timescale of the muon beam being stored in the storage magnet. You can see it on the right-hand side. The vertical gray lines indicate when the muons are in the beam. But to avoid causing discharges, what we actually do is we switch off the high voltage while there's no beam in the storage ring, and so we pulse these quadrupole plates. But this pulsing actually caused mechanical vibration of the electric conductors, which in the end caused the perturbation of the magnetic field. And this magnetic field perturbation was as large as like roughly plus minus 400 parts per billion. And this is a huge effect compared to our error budget, right? And so this is one of the other effect that took us so long to analyze, because we actually had to build dedicated NMR probes with special heads that we actually could employ inside these electrostatic quadrupoles without sparking or ruining our NMR probes. And then these measurements are actually performed in a synchronized beam mode with the beam, delaying basically the time of measurement relative to the beam injection. That's how we were able to reconstruct that pattern. We only detected this effect after run 2, and so we had to put a very conservative limit on this effect, and we had to correct by 70 parts per billion the measured field or the extracted field with a large uncertainty of roughly 90 parts per billion. The second transient that we have to deal with is from the kicker. And I mentioned before that our kicker tries to put the muon beam onto the storage orbit in 150 nanoseconds. But this means that actually this powerful kicker actually induced eddy currents in the vacuum chamber walls. And you can see the kicker plates in the picture on the right-hand side. And so we had to develop, to measure this effect of the eddy currents, a Faraday magnetometer. It was done in the group of Dave Kewal, and it's a device that is completely fiber-based. It's non-conducting because you want to have it living in between the kicker plates. It has to be non-magnetic because it's in the 1.45 Tesla field, and so it's a 3D printed structure that actually contains TGG crystals, the wave plates, the polarizer, and beam splitters. We were able to measure the effect then and model it with a single exponential decay function after the kick. You can see this on the right-hand side and the bottom. In gray is indicated the storage time of the muons, and you can see that there is a systematic change of the magnetic field after after the kickers have fired. We have weighted this effect by the kicker coverage, which is roughly 8% of the full circumference of the magnet, and with the spatial muon distribution. And so we have to introduce a correction of roughly 27 parts per billion with an uncertainty of 37 parts per billion. And so I walked you through basically all the different effects that we have to take into account to extract a mu. There's one factor that we haven't talked about, which is the clock that I said we were blind to not bias our analysis. So this clock blinding factor on hardware level was actually set in 2018 by two Fermilab science managers, Greg Bock and Joe Lycan, and they just detuned the frequency of the nominal 40 megahertz reference clock in the experiment in a range of plus minus 25 parts per million. So compared to the 0.5 parts per million statistical uncertainty that had been anticipated, it's a factor of 50. And they locked basically the panel of the clock, wrote down the number in an envelope and sealed it. And only once we have basically put everything together and we were ready to unblind in this meeting on February 25th, we opened the envelopes. And in the next slide, you will just see a couple of numbers. And I want you to pay attention to the number that starts with 39. This is basically giving you the real clock frequency that the experiment was running at. And I will just leave the next slide running for you to enjoy the moment, because we actually recorded the unblinding and the revealing of the result.
7844.
Same number. Yay.
Yep. It's the same number.
And this is what we get.
Whoa!
Wow! Oh, wow! Oh my God!
We confirm 821.
And so you see within seconds, basically, after we typed in the number in the prepared script, we had the result on the screen, and that is also what we then published. And so let me summarize this, the results from our measurement. In the first run of the Fermilab experiments, we have now extracted a value for omega A, which is slightly decreased uncertainty of roughly 470 parts per billion. And you can see this in the plot on the left-hand side, which is fully statistically compatible with the predecessor experiment at Brookhaven. And both of them are completely dominated by the statistics uncertainty. And so it's safe for us to combine these two results and provide a new average, world average. And this world average has an uncertainty of roughly 350 parts per billion, which is on par with the theory prediction. And so this is now a 4.2 sigma discrepancy between the experiment and the community approved standard model prediction. So let me come to my summary. For the very first time in 20 years, we have improved the uncertainty on the g-2 measurement of the muon. The run 1 only presents roughly 6% of the ultimate data sample that we plan to take. We already have a 15% smaller uncertainty than the Brookhaven experiment. And standing alone, we would have a 3.3 sigma tension with the standard model. But really important is that after 20 years, we confirm the Brookhaven results independently, and we can combine these two experiments and have a 4.2 sigma tension of the standard with the standard model prediction. And I checked just before the seminar, as of today, there's more than 40 preprints on the archive with updated ideas and constraints how to actually interpret our result. And so thank you very much for listening, for having me in the seminar today, and I'm open for questions.
Thanks a lot. First, let me congratulate you on the great results. And now people can ask questions. You can raise your hand if there are questions. Oh, there's one from Nacho.
Hi, thanks very much for the very complete talk. I enjoyed it very much, especially Considering I'm an outsider of the field, I enjoy very much the result in the exposition. I had a couple of questions, and bear with me because, as I said, I'm really not from particle physics. Well, the first is a pretty generic one, and it's concerning the evolution of the experiment. So do you think you're going to hit eventually the systematics floor with the increased statistics? What is the planning for the number of runs? And
yes, I think we will hit the systematics uncertainty. I'm sorry I didn't have put the backup, I think, for the plans in, but right now we are still running in run 4, and in fall we will start another round. So we have a run 5 in which we then will be able, if everything goes according to plan, to accumulate the more than 20 times the statistics than Brookhaven that we really need. So it's basically the plot here. Let me see. I had it the evolution here. You can see it. So this will still run to end of, beginning of July, and then we will have run 5.
Okay, so but the error was like currently is around so the statistical error is around 300 or 400 parts per billion. Is that it?
The combined 1 hours is on the order of 470. Yes.
Okay.
Only the small fraction here of the 6%.
Right. So and by the end, so this is a factor, an order of magnitude.
Our goal is to go down to 140 parts per billion.
Okay. Yes, that's when I went. Okay. And then concerning, this is something that I think we talked internally in our group recently, concerning the combination of the Berkeley and the Fermilab experiments, given that there's a part which I wasn't aware of, there's a part which is common, right? Which is the actual experimental apparatus. So is there some kind of covariance that one has to take into account in order to make the combination? So maybe it was considered there in that combination there.
It was considered. So there's 2 arguments to that. What you see, the only common part of the instrumentation between the 2 experiments is the magnet.
Right, the magnet. So maybe
everything else was completely built from scratch, new. The magnetic field measurement devices, the calorimeters, they are all state of the art, like 20, let's say, electronics after 2010 and after, and we have much more data that we actually store away and have more sophisticated analysis. Plus, we also have a completely end-to-end simulation or beginning to end simulation of the experiment, which was just not available at Brookhaven. And we went through the individual contributions where things could still be like common, like the kicker or the inflector magnet, and we did not find any relevant correlated effects in the results of both of the experiments. But there was a whole exercise to go through this, yes.
Yeah, I was assuming so. I just wanted to. And if I'm allowed, I guess finally, just if you had any comment on I mean, on the theoretical side, of course, I guess you were expecting this question, but what is it's a more general question. So from your point of view, the discrepancy from theory, that's really on the theoretical or computational side right now. Do you have any opinion on the alternative theoretical measurement for the anomaly?
So I mean, I think you want to refer to this result, this lattice.
Yes, the DBMW or whatever it's called.
I presented you this hadronic vacuum polarization effect.
Oh yeah.
And there's 2 methods that are initially like well suited to provide a prediction or contribution for the hadronic vacuum polarization effect. And this is this R ratio method where you take like experimental input data and then analyticity and unitarity basically, and within the standard model and try to predict these contributions. the complementary approach is the lattice. If you do a lattice QCD calculation, but these just start to mature. I mean, this is a very new result that has been put on the archive last year and was then published basically the next day, I think, from our result. And you can see this on the left-hand side here. The R ratio values in red, they have very small error bars right now. And this is what has been taken over more than 2 decades, has been developed. And then you have the lattice contributions. And this is the very first one that really brings up with a small error bar this new contribution. And I mean, from my experimental viewpoint is we just need to have independent confirmations of this new result by other groups to see what we take away from it.
Okay, yeah, thanks for the insight. Yeah. Nice.
Thanks. Are there other questions? I can ask myself, from these more than 40 preprints that appear, did you find anything promising, anything new? I mean, we were kind of expecting a lot of theory papers appearing.
Yeah, I mean, like, it's interesting, I think, to see what is maybe not. I mean, but there's really a lot of proposals. I mean, in particular with the announcement of like 2 or 3 weeks ago from LHCb that you might have another anomaly detected in the decay of kaons. This is one model, but me as an experimentalist at that point, like, my attitude is we just need more of the experiments to really figure it out what's going on, and complementary experiments. Even if we establish like a discovery at the 5 sigma level, we still need other experiments like mu gamma, mu23E, mu2E to really understand what the underlying process would be.
Can you elaborate a little bit more on other experimental possibilities?
So, I mean, the mu gamma experiment, for example, at PSI is searching for the lepton flavor violating decay of a muon just in an electron and a photon, right? This is a process that's forbidden in the standard model. And depending on what the underlying physics would be, you test different parameter spaces of extensions. Another experiment going on at PSI is the search for the decay of a muon into 3 electron type particles, mu23E. And our sister experiment at Fermilab is looking at the conversion of muons in the nucleus into an electron. So this is mu2E, which is built in a building next to ours and is basically in its commissioning phase. And so we need the results from all these experiments to nail down which of the modifications or extensions of a standard model would be the right one.
Yeah, could be interesting to see. We have a question from Isabel.
Hello, thank you very much for the seminar. It's really impressive. Going back to the reduction of the expected reduction of in the uncertainty at the end of round 4, or the ultimate precision you want to reach. I understand that most of it is because you are collecting a lot of statistics. But then from the pure systematical side, you showed a lot of effects that you have evaluated. Few of them, they were a small correction, but with a large uncertainty. In a couple of them, the uncertainty was even larger than 100%. So from the pure systematical side, what is your ultimate expectation? Because most of the reduction is statistical, so this will certainly be reduced.
Yes. So
after,
you see my slide still, right?
Yeah.
So the largest changes that we're gonna have is the electric field contribution, which will be smaller because we can center now the beam, and I forgot, sorry, to put your plot in there, on its nominal storage orbit. So this correction will be smaller, and also the uncertainty will be smaller. The phase acceptance effect was purely there because we had these broken resistors in run 1. So this will be eliminated just by the upgrade of the resistors, and the beam is much more stable, these conditions. So these are on the omega A side, these are the largest contributions. In the magnetic field side, we will have better and more frequent measurements and characterizations of these effects. We were only able to measure these contributions partly at some points in the kicker and the electrostatic quadrupoles, and we want to have a full map basically of this effect across the whole storage volume. These are aspects that we're going to improve.
Mm-hmm. Impressive. Congratulations.
Thank you.
I don't see more questions. Well, I guess we have no more questions. Let me just congratulate you once more. Thank you for giving the seminar so close to the result release.
Thank you very much for the invitation and the opportunity to talk here. Thanks a lot.
And let me announce that we will have another seminar next week of Juan Calderón about LIGO and the gravitational wave signal consistent with a compact binary merger, and we will send you the the abstract and the indications. And thanks to all of you.
Thank you. Bye bye.
Bye.
Thank you.